Hello, good morning. This is Mr. Hausman, and this video is being made for my G Block Physics in 2022. I'm sorry I can't be in school today, but I just need to be in Connecticut taking care of some family members, and all is well. And I should be back very soon. So thank you for taking on this important work as independently as you can. I've seen most of you for the start of this lesson on forces, and some of you may be able to skip ahead a few minutes. If you already giving it your best, this work, maybe you already have this packet completed on this page. Okay, there's going to be a few minutes of this, and then we're going. So thanks very much for. Okay, so number one. Most of us have been here and examined what is going on with forces. And we've heard about this idea of inertia, but let's fill in any gaps that we might have. So this is the stuff we've already done this year. We've studied motion from the ideas of displacement, time, velocity, and acceleration. And what these have in common is they are describing what happens to an object when it moves. But the question that we're being asked next is why is it moving? And that is called dynamics. And dynamics are when we study how forces cause changes in the motion. What that really means is how do forces cause you to accelerate or objects to accelerate? So a force is really just any influence. It could be how cars push on a road. It could be how a person lifts weights. Many forces exist in nature and in our daily lives, but it's an influence which tends to change the motion. And we use forces all the time, from walking to driving and everything in between. So forces, lastly, are one of our many vector quantities. So as soon as it's a vector, then it has a direction to it. So how do we describe a force? Well, you can creatively think of a force as just any push or any pull. And there's no limit to how many forces can act on an object. You could have 4 forces, 5 forces. And this could be a generic object, and we might describe it as having maybe a force holding it down or pulling it down, maybe a force that supports the object that keeps it from falling. We could pull the object to the side. Maybe there's even friction to the left. Now, I mentioned some forces, but you don't have to put those all in because we'll examine those shortly. The unit for force is newtons. It's named for Isaac Newton, and the symbol is a capital N. Because force and acceleration are both vectors, that means when we talk about a force, we're going to have to think about how big is the force, right? Its size. Is it a big push? Is it a small push? Is gravity a strong force or a weak force? And we're going to also have to consider what direction it travels. It moves. Is it pulling you to the right? Is it pulling you up? Is it down? Okay. Down the road, we're going to examine that forces fundamentally can be described as either contact forces, because the two objects are directly touching, like an applied force, like a spring force. Springs have to be touching an object to pull or push on it. Even friction requires contact. And then there's these guys. These are forces that used to be called spooky. Uh, they're not really scary, but they are really much more complicated to explain. Explain to me how the moon out there in space orbits the Earth, but yet never touches the Earth. How do we know that it is being pulled toward the Earth by gravity? And it may just be something you take for granted, but we do know how some of these work. Electric forces are how positive and negative objects attract or repel, depending on what charge they have. And magnets, well, when you were a little kid, I'm sure most of us have played with toys that have magnets in them, and they can attract each other. And there's definitely like an aha moment, as well as this page. Certainly skip it, progress to, okay. Okay, so let's start motion with understanding that there are 3 laws. three laws that Isaac Newton put forward. And the first law is the law of inertia, and it has to do with balanced forces. Okay, balanced, meaning like, things are even. So take for a minute, you've got an Amazon package being shipped to your house, maybe for the holidays, and it's sitting there at rest on your front porch near your apartment by your house, whatever it might be. Is it going to ever start moving by itself? What would it take to make it start moving? Well, we know that objects at rest, they need a force, right? What would make an object start moving? The answer is a force. Okay, now if you believe that to be true, that you need a force to start it moving, let's take a look at something that was done really famously by another old guy named Galileo. And we can do it as a thought experiment because this is actually really hard to do in real life. Can you imagine a ramp? It looks like a half pipe from like skateboarding, but it's more of a V shape. But it has zero friction. Maybe it's made so smooth that the ball rolls silently, it doesn't make any noise, and it rolls down and it then comes down to the bottom, and then another force slows it down as it goes back up, right? But it always goes to the same height. Then if you change the shape of the ramp and make it a little less steep, do you see that that's almost the same scenario, but just less steep? We've lowered the angle. Do you agree that the stopping point would be the same height? Well, I think so. They would get to the same height. Okay. Now, what force would make it stop at the bottom? And this is on a frictionless ramp. And the answer, therefore, is there's no force acting on it to stop it, right? No force stopping the ball, the rolling ball. So this led Galileo, this simple thought experiment. Some people say he actually made this ramp in a workshop, and he kind of noticed that when this ball is rolling down the hill and it's moving really fast on the flat part, he knew that there was forces acting on it, but none of them were sideways. They were all vertical forces. There's no force sideways ever going to stop this ball. And this led him to coin the term, which means to come up with this word. We call it inertia. And usually he knew that friction was a stopping force. But the key idea is that Newton later, many years later after Galileo, he took this idea of inertia and he declared that basically that you don't need a force to keep moving, you need a force to stop moving or to start moving. So that a force is not needed at all to keep it moving, only to change its motion. And that was huge. And I bet you've heard this called the law of inertia. An object at rest tends to stay at rest, and an object in motion with a constant velocity. Maybe you've never heard it said that way, but it's a constant velocity. So there's two parts. An object at rest stays at rest. An object moving with a constant velocity will continue that way. Now, this is not forever. It happens until there's an unbalanced force. So the soccer ball is at rest, and the moment you kick it, it's World Cup season in 2022, and there's been a lot of goals scored. I've got my favorite is probably France. A lot of people think France has got it this year again because of a player named Mbappe, and he scores a lot of goals. So, you kick the ball, and you've changed its state of being. A force was needed to change its inertia. Newton's third rule. Okay. So mass is related to inertia. We've all heard of mass. Mass is how much matter you have. Inertia is an object's resistance. So if you have inertia, you have resistance to changes in your motion. Think about tablecloths. Remember the tablecloth and the big heavy bowl that we put on top of it? And we pulled the tablecloth to the side and the bowl stayed at rest? Well, that was because it had a lot of mass. It had a lot of inertia. So mass, in a way, besides measuring how much matter you have, is related to the amount of inertia you have. The more mass you have, the more inertia. So we, of course, know that mass is measured in the unit of kilograms. Okay? And, it's you go to a scale in a classroom and you measure it, maybe a kitchen scale. Now, there's another weird idea that we often talk about, and that third idea, not inertia, not mass, is weight. And let's be clear about that. So let's not get these two confused. When you know the mass of something, you know how much matter it has, how much inertia it has. But your weight, that's actually that's a changeable subject. And I don't mean because you gain or lose weight. I mean because the weight of an object, which really is the force of gravity, changes depending on where you are. So the force of gravity that you have on Earth is very large. Your force of gravity on the moon is 1/6 the force of gravity or the weight on Earth. However, what never changed is this person's mass was still 56 kilograms, right? Going from place to place. So an object's mass is constant. And this is no matter where you go in the universe. Weight is a variable, meaning weight is a measure of the force of gravity. And weight depends on what planet you're on or planetary object. Moons aren't planets after all. Okay, so hopefully we're doing well with a few ideas having to do with forces and inertia so far. Law. So here's the page. I want you to hit pause. I want you to answer these questions. They are a little bit more than yes or no answers. Some of them you have to circle, but there's room to answer the first question, the second question, and then there's, let's see, a couple more here. So please try all of these, and you are going to submit a picture of your answers to these questions. Now, if you get a little stuck, well, at least the bottom 5 aren't answered here. Here's the key. So you'll turn your page over and see how you did on those questions. But try them first, do it honestly, and do your best job. It pulls on you. That's here on slide 6, and then eventually a kind of a glossary of forces. And that way we can progress with our lessons when I'm back. Okay. So we're going to continue with this lesson. This is the third law. And the third law is, and it's weird that we're going first, the third law. The second law, that's got some depth to it. So we're going to go into that one next when we're together. But Newton's third law is about forces that are together. And we call those force pairs, right? If you're a pair, that means there's 2 of you, right? Forces come in pairs. It's a classic phrase that I want you to kind of just connect. You cannot have a force all by itself. The weird thing about this is that it doesn't mean that one object has 2 forces on it. It means that there has to be 2 objects. Let's call them A and B. And they are going to experience always equal and opposite forces. And you could say that with symbols by saying A is object A and B is object B. So there's a force of A pushing on B. And therefore, do you see how the letters switched? They changed their order. Now B pushes back on A, but there's a negative sign. That's a way of saying opposite. Okay, there must be force vectors acting on 2 objects, not just one. You have to have 2 objects. So here are some examples. So your hand is pushing against the wall. So if someone said, tell me about the forces on the wall, you would say it would be the force of the hand on the wall. And probably you'd say that's to the right. Then the wall pushes back on you. So that's the force of the wall on your hand. And what is this little box? That represents the object, the wall, right? If you want to draw it like this, that's okay. And then here's your hand. That's it. Look like it says hard, but that's the wall in your hand. Here's a weird scenario. What if you take a rolling chair, you got wheels, and you have one friend, I don't know, put their feet up on your knees, and this person is attached to the floor. Their feet are planted. So we've got the pusher, and we've got the other person, right? The non-pusher. So those are the 2 objects that are interacting, right? They're both nouns. So the pusher experiences what force? Well, he or she pushes on the knees, and the pusher ends up getting pushed backwards. And the other person feels a force into them, but because maybe their feet are stuck to the floor, they don't actually go anywhere. Here's another classic one that people always get wrong. Okay, name the force pairs. We're looking for pairs of forces on you and the planet Earth. Okay, and you probably take for granted that, let's use red, that Earth pulls you downward. We just know it happens. And you go, okay, so what's the force? What's the opposite force? Well, if one object is you and the other is the Earth, remember all you do is turn it around. If Earth pulls on you, then you pull on the Earth. And it's hard to believe, but you pull on the Earth just as much. So, which way do you get pulled? Well, you get pulled inward. Sometimes we say that's downward, right? You get pulled downward toward the Earth, right? Toward the center of the planet, really. But the Earth gets pulled upward by you. These forces are equal and opposite. You have just as much pull on the Earth as the Earth has on you. And then maybe even a more abstract one is, what if you have a balloon and there's air molecules bouncing around inside here? You've inflated it with your hot air, and the air molecules feel what? Well, they get squeezed inward. They're bouncing around, but there's a balloon that's pushing inward on those. And that's, so the air is interacting with maybe it's a latex balloon or one of those shiny metal balloons called mylar. The balloon, on the other hand, is feeling equal and opposite forces outward. Okay. There's a few details on the bottom of the page. I'd like to go over those together maybe. The fins push on water, and the water has to push back. That's how fish swim through the water. Birds flying through the air, well, the bird's wings push the air, even though we don't think of air as being actual matter, it very much is. And the air must be pushing the bird upward. So I'll leave that there. There's another example. The car pushes on the road and the road pushes on the car. Okay, we're going to come back to this one at a later date. And that is a great place to wrap things up. So thank you for watching. Thank you for completing page 5. And we'll take a look at how the third law works when the masses that they're acting on are very different, such as the Earth and the human, or in the case of a cannon and a cannonball, okay, or a baseball bat and a ball, right? They still experience equal and opposite forces, but they have very different outcomes.